Welcome back to the Deep Dive, where we take a stack of sources and distill the fundamental knowledge you need fast. Today, we are focusing on a seismic shift happening in modern medicine.
We really are. It's the revolution of massive data, specifically in diagnostic pathology.
Right, a field that for, a century has been defined by the human eye on a glass slide.
And now it's rapidly moving to a digital environment, things like whole slide imaging. And this provides the perfect computational canvas to start applying AI and deep learning directly to, diagnosis and patient care.
And our main source for this deep dive is this really key academic monograph called Artificial Intelligence and Deep Learning in Pathology.
And what's great about it is that it was written specifically to be a bridge. It gives physicians and medical learners the essential knowledge they need about these technologies.
And crucially, with zero required background in advanced math or programming.
Exactly. So our mission here is to give you that roadmap. We're going to unpack the core concepts, AI, machine learning, deep learning, and define those often confusing overlapping terms.
And then show some concrete, real-world clinical tools that are actually moving from the lab bench to the patient's bedside.
Let's do it.
Okay, so let's start with those foundational definitions because AI, ML, and DL get tossed around interchangeably, and it makes it hard to know what we're actually talking about.
Right. So artificial intelligence, or AI, that's the biggest umbrella. It's the broad scientific effort to, enable machines to mimic human intelligence in performing tasks.
So the whole concept.
The whole concept. Now, machine learning, or ML, is a specific subset of AI. It focuses on algorithms that learn patterns and make predictions from data.
And they do that without needing explicit, handwritten instructions for every single task.
Precisely. So if AI is the concept, ML is the method of getting there by feeding it data.
So then, what makes deep learning so special?
Deep learning is a specific type of ML, a really powerful one. It uses what are called neural networks.
Simulated layers of connected neurons.
Exactly. And the key is that the input and output are separated by multiple hidden layers. The term deep just refers to that multi-layered architecture. It's what allows it to handle really complex data, like a high-resolution image.
To really get the power of these learning models, we have to look at how a computer normally works. The sources spend a bit of time on the computer's basic vocabulary.
Yeah, things like assignment.
Right.
In programming, the instruction x equals 5 isn't a statement of mathematical equality, it's an order. Assign the value 5 to the variable x.
Which is why something like x equals x plus 2 makes perfect sense to a computer.
It takes the current value of x, adds 2, and then assigns that new value right back to x.
And the other core piece is conditionals. Simple if-then logic.
Which leads us right to the crucial difference. Rules-based programming versus machine learning.
Okay, so give us an example.
Think about calculating pi. A classic rules-based approach uses an infinite series, or maybe that Monte Carlo simulation.
Where you're sort of throwing random darts at a target.
Right. In both cases, the formula, the rule, is predefined. It's baked right into the code. The computer is just following instructions.
With machine learning, the rules aren't predefined.
Exactly. Instead of following a rigid formula, the system takes in huge amounts of data, let's say images of cancerous and healthy tissue, and it automatically makes inferences. It discovers the patterns that differentiate the two.
It derives the rules from the data itself.
It does.
Well, that immediately raises a question for me. If the computer is making its own inferences, how do we evaluate if those are reliable? For a patient, I mean.
That is the million-dollar question, and it's where we run into the massive problem of using simple overall accuracy.
Because it can be completely misleading, especially in medicine.
It can. Do you want to walk through the classic example?
Yeah, so take a rare disease, maybe an aggressive tumor, that only occurs in, say, 1% of the population.
A very common scenario.
Right. So a totally useless algorithm can get 99% accuracy just by classifying every single patient as healthy.
The accuracy score is amazing, but the tool is worthless. It missed every single real case.
A critical point, especially since so many diseases we're trying to find are rare. So if accuracy is out, what do we look at?
We have to rely on metrics that come from something called the confusion matrix. It breaks down all the decisions.
True positives, false positives, all that.
All that. And the two most critical metrics that come out of it are precision and recall.
Okay, so let's define them. What is precision?
Precision, you'll also hear it called positive predictive value, or PPV. It measures exactness. It answers the question, of all the cases the model flagged as positive, What percentage were actually positive?
So it's a measure of trust. If it says positive, can I believe it?
Exactly. High precision means you can, and then there's recall.
Or sensitivity.
Right. Recall measures completeness. It asks, of all the actual positive cases that really existed, how many did the model find? This is critical for screening. You do not want to miss any true cases.
So you want to avoid false negatives.
You want high recall. And often when you're evaluating a model, you'll look at the F1 score, which is a kind of balanced average of both.
Knowing those metrics is one thing, but the data you feed the model, that's maybe even more important.
Oh, absolutely. Which brings us to this stunning real-world example of data bias from the sources.
The sepsis readmission study.
Yes, at Chicago Hospital. So researchers noticed that patients with dangerously low pH levels, meaning they were very, very sick, were somehow less likely to be readmitted.
Which makes no clinical sense at all.
None. The reason? The training data included patients who had died during their first hospital stay.
Ah. And since deceased patients obviously can't be readmitted, the algorithm learned to associate low pH with not readmitted.
It created a statistically significant but fatally flawed connection. It's a perfect example of how algorithms find correlations, not causation.
And it shows how vital the medical expert is in curating that data. Without that clinical oversight, you could deploy a really dangerous tool.
You really could.
So moving from data to methods, let's touch on shallow learning models. These sort of laid the groundwork before deep learning really took off.
Many of them are based on geometric models. A simple one is k-nearest neighbor, or KNN.
Okay.
Imagine we're plotting tissue samples on a graph based on two features, like cellular size and nuclear density. A new sample lands near the boundary between two classes. What does KNN do? It just looks at its k nearest neighbors, say the closest 5 samples, and it gets assigned to whatever the majority class of those 5 is.
Simple enough. What about something more complex, like a support vector machine, or SVM?
An SVM tries to find the single best boundary line. It's called a hyperplane that creates the biggest possible separation between two classes.
And it only focuses on the data points closest to that boundary line, the support vectors.
Exactly. And what makes SVMs so powerful is something called the kernel trick. If your data is all jumbled up in 2D, the kernel trick can project it into a higher dimension, like 3D, where suddenly you can separate the classes with a simple flat plane.
That's a clever way to handle messy data. We should also mention unsupervised learning, like k-means clustering.
Right, and k-means is different because it works on unlabeled data. You're trying to find inherent structures.
So you don't know the right answers ahead of time.
You don't. You just tell it how many clusters, or k, you want to find. The system guesses some center points and then keeps assigning data points to the nearest center until the clusters stabilize. It's a way to find natural groupings in your data.
Okay, so now we get to the real engine of this revolution, deep learning. And the big strength here is moving from feature engineering to feature learning.
This is the core difference. With shallow learning, a human had to engineer the features. You had to explicitly tell the machine, look for lesion area or measure nuclear shape.
But deep learning doesn't need that.
It bypasses that bottleneck completely. The neural network automatically figures out which features, from simple edges all the way to complex architectural patterns, are important for telling a benign tumor from a malignant one. It just abstracts them from the raw pixels.
And because this learning happens deep inside the network's hidden layers, we get the term black box, which in a clinical setting causes a lot of concern.
It does, because the process is often initiated randomly and becomes partially unexplainable to us. We know the math works, but tracing the exact rationale for a decision is hard.
The sources make a great analogy for this.
They do. Ask an experienced pathologist how they made a really complex diagnosis. Even they might struggle to articulate the precise cognitive steps. It's an intuitive black box for the human expert, too.
So if the system is learning without explicit rules, how do we actually teach it?
Through a process called backpropagation. It's a type of supervised learning. You feed the network data that has been labeled with the ground truth, the correct answer.
Okay.
The network makes a guess, an output, and you compare that to the ground truth. The difference is measured by a loss function. The system then works backward through its layers, tweaking the connections to minimize that loss until its guesses consistently match the right answer.
And for image analysis, which is everything in pathology, the champion architecture is the convolutional neural network, the CNN.
CNNs are just brilliant for images. They use these things called convolutional filters. They're like little digital magnifying glasses that slide across the image to find specific features. edges, textures, things like that.
And then the pooling layers come in.
Right, after convolution, pooling layers like max pooling summarize whether those features were found in a certain patch of the image. This whole process makes the network really good at recognizing structures no matter where they are in the picture.
So let's shift to some of the more advanced architectures. Not everything is about classification. Some models, like GANs, are about creation.
Right, generative adversarial networks. They're designed to generate things like hyper-realistic synthetic images of tissue, and they work through this ingenious adversarial process.
Two competing networks.
Two networks. You have the generator, which tries to create fake examples, and the discriminator, which tries to tell if an image is real or fake. They're locked in this game, and it forces the generator to create increasingly perfect, undetectable forgeries.
And then there's reinforcement learning, RL, which is a totally different concept.
Yeah, RL is inspired by operant conditioning. It's for sequential decision problems, like teaching a system to play chess or Go. The system learns by trial and error. The reward signal is delayed. It only finds out if its sequence of moves was good at the end of the game.
While all this is amazing, the monograph is very clear about 3 critical limitations of current AI.
Yes. First, limited generality. They are one-trick ponies. An algorithm trained on liver fibrosis can't analyze kidney disease. They lack general human intelligence.
Second is the data hunger.
Extreme data hunger. They need thousands, sometimes millions, of expertly labeled examples. A human toddler can learn the difference between an apple and a pear with just a few examples.
And the third limitation, computational cost, is just staggering.
It really is. Training these huge models is incredibly energy intensive. There are estimates that training one large AI model can produce carbon emissions nearly 5 times greater than the entire life cycle of a car. That's an ethical and logistical hurdle we just can't ignore.
Which also means we have to look closer at bias. The sources draw a really clear line between 2 types.
Right. You have coding or model bias. This comes from assumptions baked into the algorithm itself. For example, a simple model might assume all features are independent, which in biology is almost never true.
And then there's the much more insidious data bias.
This is when the training data itself reflects unfair societal prejudice. There was a famous example of a healthcare algorithm that used past costs as a proxy for how sick a person was.
And that failed because unequal access meant that Black patients often had to be much sicker than white patients to rack up the same level of costs.
Exactly. So if you use that algorithm to allocate resources, you would just amplify the existing health disparities. It's why explainability, understanding why an AI made a decision, is so crucial for clinical adoption and for regulatory approval.
This brings us right to the practical reality of AI in pathology today. And the catalyst for everything is the adoption of whole slide imaging, or WSI.
WSI is the foundation. By digitizing entire biopsy slides, we create the platform we need to apply machine learning at scale. Without WSI, none of this really happens.
So what are the main tasks AI is tackling in this new digital world?
You can group them into 3 buckets. First, classification. Is it benign or malignant? Second, segmentation, which is identifying and outlining specific regions of interest.
And third is image translation and enhancement.
Exactly. And with segmentation, it's helpful to know the 2 types. There's semantic segmentation separating broad classes like tumor versus stroma. And then there's instance segmentation, which is incredibly granular. It identifies and counts every single unique element, like every single nucleus on the entire slide. That's a level of detail that's just impossible for a human to do consistently.
And image translation. That sounds like a lab problem.
It solves critical variability issues. Stain color normalization can reduce color differences caused by different scanners or protocols between labs. And even more exciting is mode switching.
What's that?
It's where AI can convert an image from a novel imaging method, like quantitative phase imaging, into a familiar H&E-like image. You could potentially eliminate the need for time-consuming chemical staining altogether.
Okay, let's talk performance. The sources give a great clinical example with prostate cancer grading the Gleason score.
Right, so deep learning systems have been trained on this, and the results are impressive. In one study, a DLS got 70% accuracy on Gleason grading. The average for pathologists was 61%.
And it even performed better than pathologists with less than 15 years of experience.
It did. It shows the potential as a really reliable second opinion. But, and this is a big but, there's a bottleneck.
The training data.
The training data. To get that level of performance, one effort required pathologists to annotate 112 million individual image patches. That took almost 900 pathologist hours just to label the data.
Wow. Scaling that up is the huge challenge.
It is. But the ultimate payoff isn't just about replicating a human. It's about finding information that's invisible to us. Predicting a patient's molecular status, their genotype, based only on the visual morphology, the phenotype.
That's working backward. That's the future.
Absolutely. A key example is analyzing tumor-infiltrating lymphocytes, or TILs. AI can generate these quantitative tumor TIL maps on H&E slides, counting every single immune cell in and around the tumor. This is vital for predicting if a patient will respond to immunotherapy.
A human could do that in theory, but not across hundreds of slides accurately or fast enough to be useful.
Exactly. The monograph says it would be prohibitive due to the amount of labor, time, and cost. AI makes this kind of prognostic information instantaneous and actionable.
Amazing. Okay, we've covered a lot. The definitions, the challenges, the clinical reality. Before we synthesize, here's a quick review question for you, the learner.
Yeah, let's see what's stuck.
Okay, imagine this. You're a medical learner evaluating a new model for a rare tumor, less than 2% incidence. The manufacturer is proudly advertising 98% overall accuracy.
Which sounds great on the surface.
Right, but before you would ever recommend it for clinical use, which two key metrics beyond accuracy would you absolutely insist on seeing, and why?
The answer has to be high precision and high recall. You'd insist on them because 98% accuracy is meaningless for a rare disease. You need high recall, or sensitivity, to make sure you're catching all the rare cases and not having dangerous false negatives.
In high precision.
And high precision, or PPV, to ensure that when the machine does flag a positive case, you can trust that it's not just a false alarm.
Perfect. So what does this all mean for the future of the pathologist?
Well, the core conclusion from the work is really clear. AI is not going to replace the pathologist. It's going to serve as an indispensable digital assistant.
Handling the repetitive, the quantitative, the data-heavy tasks.
With inhuman speed and consistency. The future is the synergy of human intelligence, HI, combined with artificial intelligence, AI.
And the most fascinating potential, and the provocative thought we'll leave you with, is AI's ability to detect subtle visual cues that are invisible to the naked human eye. This lets us work backward from the observable image phenotype to the underlying genotype that actually drives a tumor's behavior.
And that ability to link morphology to molecular biology, that is the future of truly personalized precision medicine.